In this video, we're going to talk about solving systems of inequalities. And in this section, we're going to be dealing with nonlinear systems of inequalities. So previously in your algebra, your pre-calculus algebra class, you solved systems of inequalities and you graphed maybe two lines. One was solid because it may have been less than or equal to or greater than or equal to. And one might have been dashed because it would have just been a greater than or a less than. And then you might have looked at shading on one side of the line as well as on the other side of the other line. And your solution would be that region where you've shaded twice. So we're going to be doing the same thing. We're just going to be solving a system of nonlinear inequalities. And we're going to graph them and shade. And we'll also find that point of intersection, that vertex point. Couple of things to keep in mind. You're going to draw a solid line if you're greater than, equal to, or less than equal to. If your inequality sign has an equal included, that's going to be drawn with a solid line. And if you do not have an equal to, if you just have a greater than or a less than, you need to make sure you are drawing a dashed line. And if you're doing this on your homework using a computer program and you're graphing these, there's an option to toggle between solid and dashed. Please just remember to do that. All right, so essentially all that inequality sign is doing is telling me where to shade. So I'm going to go ahead and treat these like an equation. So I have y equals 1 minus x squared and y equals x minus 1. Now, what do the graph of these look like? Well, we have a parabola opening down, shifted up 1 unit, and then we have a line with a slope of +1 and a y-intercept of -1. I'm going to go ahead and sketch those, and you have a graphing calculator. You can plug these into your calculator and see what they look like. So our parabola shifted up 1 unit, opening down, looks roughly like this. And my straight line, slope of +1, y-intercept of -1, looks roughly like this. Now, notice I went ahead and drew my line with a dashed or dotted line because I didn't have an equal to there. So now we're going to be looking to solve. We can see graphically where those solutions are, but we're going to solve algebraically for these 2 points of intersection. We also need to determine where to shade. Is it inside where they're both overlapping? Is it out here? Down here, we've got a lot of different options to choose where to shade, where the solution set, where all of the points would satisfy both of these given inequalities simultaneously. So let's look at solving this algebraically. First thing we want to do would be to say, are we going to use the substitution or the elimination method? And since these are not organized or we don't have squared terms in both, I'm going to use the substitution method. And one thing I notice is that both of these equations are equal to y, which means both right sides are equal to each other. So I can write the equation x minus 1 equals 1 minus x squared. So now I'm dealing with a quadratic polynomial. When we're dealing with anything that's quadratic, we always want that in descending order equal to 0. So I'm going to add the x squared over to the right. I've got x squared plus x. And I'm going to subtract this 1 over on the right, x squared plus x. -1 minus 1 gives me -2 is equal to 0. So now we can factor this. This would be x plus 2, x minus 1. And of course, that is equal to 0. So we have x plus 2 equals 0, or x minus 1 equals 0. That's by the zero product principle. And that gives me that x equals -2 or x equals +1. And you can see at x equals -2, we have a point of intersection, and at x equals +1, we have a point of intersection. Now, if I want to determine the y value, well, we'll come back up here. What is y equal to? y is equal to x minus 1. So if y equals x minus 1, and we do y equals negative 2 minus 1, that gives us negative 3. So we have one ordered pair, negative 2, negative 3. And over here, y equals 1 minus 1. That gives us y equals 0. So now I have positive 1, 0. So I have two vertices, or the points of intersection, for these two curves. So I've got 2 points here. We'll call these our vertices. All right, so we're almost done, but we still need to determine where to shade. So I cleaned my screen up, and now let's look at determining where to shade. So essentially what I'm going to do is I'm going to plug an ordered pair that is not on either of my curves into both of these equations. So I might start with the ordered pair 0, 0, and I'm going to plug 0, 0 into this parabola first. So 0 less than or equal to 1 minus 0 squared. This simplifies to 0 is less than or equal to 1. Is this a true or a false statement? Of course, this is true. 0 is less than 1. So that means for the parabola, we're going to be shading below or inside, beneath that parabolic curve. Now, in order to keep my screen from getting too messy, I'm going to clean this up, but I want you guys to remember I was shading under the parabola, under, not on the outside of the parabola. Let's repeat that procedure with 0, 0 for the line. Now notice 0, 0 is above the line, so we're either going to get a statement that tells us we need to shade above or below the line. So 0 is greater than 0 minus 1. That tells me 0 is greater than negative 1, which is false. So should I shade above the line in this situation? The answer is no. We need to shade the region that is below the line, and then also the region which is inside or under the parabola, which gives me a final solution set. The area or the region where I can choose an ordered pair and it will work in either of these equations simultaneously is below, not touching that line, or anywhere underneath the parabola, or that is also anywhere underneath that parabola, and we can touch those parabola boundaries. And by that I mean if I choose any point in this shaded region below, it will work in both of my original inequalities at the same time. So any point over here, if I choose a point on the outside or above, it may work in one, it may work in neither. But in order for it to be true in this set of inequalities simultaneously, it has to be in this region. So that's it for this video. We solved a system of nonlinear inequalities, and we found the vertices, or rather the coordinates representing the points of intersection.